Okay, so it is officially 2026. And if you've been paying attention to the landscape, and I mean the actual physical landscape outside your window,
Yeah.
you've probably noticed something feels different.
Hmm.
For a long time, we thought of tech as this, intangible thing. It was software, it was the cloud, just lines of code floating around in the ether.
Right. It was basically invisible.
Hmm.
Magic that just happened on your screen.
Exactly. But looking at this stack of reports and industrial analysis we have on the desk today, it is very clear that the invisible era is over.
Way over.
We aren't just looking at a software update anymore. We are witnessing a heavy nuts and bolts industrial revolution. We're talking about a transformation that's reshaping the physical world from repurposing limestone mines in the American Midwest
Hmm.
to completely rewiring the power grids of Europe.
It's a massive shift. And to
Yeah.
really grasp the scale of what's happening right now, in 2026, we have to look at the money first, just to set the stage.
Yep.
The generative AI market is currently accelerated at about 40% annually. We're barreling toward a valuation of nearly $1 trillion by 2032.
$1 trillion.
But honestly, the dollar amount is the least interesting part of this story.
Why is that? Usually $1 trillion gets people's attention.
Because you can print money, but you can't print physics. The fascinating part, and what we're digging into today, is the physical infrastructure required to actually reach that $1 trillion valuation. We are running into the hard limits of thermodynamics, geology, and, well, electrical engineering.
And that is our mission for this deep dive. We are unpacking the physical brain of the AI economy. The headline from our sources is basically this: the data center, as we knew it,
It's dead.
it's dead. Or at least it's evolved into something so different that using the same name feels wrong. We're moving to AI factories.
That distinction is absolutely crucial. If you think back to, say, 2020 or 2022, a traditional data center was essentially a digital warehouse. It hosted websites, it managed corporate databases, maybe it ran your email server. It was predictable. You'd have a rack density, that's the amount of power a single server cabinet draws, of maybe 5 to 15 kilowatts.
Which is roughly, in household terms.
Think of 5 kilowatts as running maybe 3 or 4 hair dryers at once. It's hot, but it's manageable. You could cool it with standard air conditioning.
Okay.
But these new AI factories designed to train large language models, they are beasts. We're looking at rack density starting at 40 kilowatts and scaling all the way up to 130 kilowatts.
Wow.
There are even some extreme designs in these reports pushing 600 kilowatts per rack.
So we've gone from a few hair dryers to, what, a localized lightning strike?
Effectively, yes. These aren't just bigger server rooms. They're specialized industrial plants. And because the physics have changed, the metric for success has completely changed too.
How so?
It used to be about PUE, power usage effectiveness. Basically, how efficient is my air conditioning? Now operators are obsessed with a new metric: tokens per watt per dollar.
Tokens per watt per dollar. That sounds like a new currency. I want to make sure we really get this because it seems to be the fundamental equation of 2026. Break that down.
So a token is the fundamental unit of AI thought. It's a chunk of a word, a piece of code, or a pixel that the AI generates.
Okay.
So this metric literally measures how much intelligence can I produce for every watt of electricity and every dollar of capital I spend. It is treating electricity as a raw material that gets converted directly into intelligence.
That frames it perfectly. We are converting raw energy into cognitive output. So if we're building these massive factories to do that conversion, we have to start with the most basic constraint. Where do you even put them?
Yeah.
Because reading through this, it seems like you can't just buy a plot of land and plug in an extension cord anymore.
Not even close. This introduces what the industry is calling the power wall. For a long time, the main bottleneck in AI was chips, just getting your hands on enough NVIDIA GPUs. Now, the primary constraint is finding available electrons.
The sources mention that in the big traditional hubs like Northern Virginia or Silicon Valley, the situation is actually pretty dire.
Dire is the right word. In those hubs, the wait times for a grid connection are currently 4 to 5 years.
4 to 5 years.
Yep. Imagine building a multi-billion-dollar factory and being told, great, the building is done, but we can turn the lights on in 2031. The grid in those areas is just tapped out.
So if you can't build in Silicon Valley, where do you go?
You migrate. We're seeing a massive geographic shift. Developers are leaving those dense urban clusters and heading to the Pacific Northwest and the Midwest. It says here that data centers are projected to account for 90% of new power demand in the PJM region.
The PJM region.
Yeah, that covers parts of Virginia, Ohio, and the Midwest.
That 90% figure is staggering. It basically means the entire growth of the power grid in that region is just to feed AI.
Exactly.
But because of this squeeze, we are seeing some incredibly creative, almost sci-fi locations. My favorite example from the research is the Bluebird Underground in Missouri.
Oh, that project is fascinating. It really highlights how the criteria for good real estate have changed completely.
It's literally inside a decommissioned limestone mine, 85 feet underground.
Yep.
And the report makes it clear this isn't just for the cool factor or to look like a Bond villain lair. There's a very practical reason for burying these things.
It's thermodynamics again. Because it's underground, the ambient temperature stays constant at about 64 to 68 degrees Fahrenheit year-round. That is free, natural cooling provided by the Earth itself.
You don't have to fight the summer heat.
Exactly. Plus, you're immune to tornadoes, which, if you're building in the Midwest, is a massive insurance advantage.
It creates a natural competitive advantage.
Mm.
And we aren't stopping at caves. Microsoft has been experimenting with underwater data centers for a while now, right?
Yes, Project Natick. The idea is to use the ocean as an infinite heat sink. You drop a sealed pod to the sea floor, and the cold water just carries the heat away instantly.
And further out,
Looking further out, the reports mention serious discussions about space-based compute nodes.
space. You mean putting these servers in orbit?
It sounds wild, I know, but the physics makes sense. In the cold vacuum of space, you have infinite cooling potential, and you have direct, unfiltered solar radiation for power.
So that's the long-term play.
It's a very long-term prospect.
Okay.
Getting the heavy hardware up there is expensive, but it shows the lengths or heights developers are considering to escape the power wall on Earth.
Okay, so if you are a developer in 2026 and you aren't ready to launch rockets, how do you even find a viable spot? You can't just drive around rural Ohio looking for sale signs.
No, you use AI to build AI. This is where GeoAI or geospatial AI comes in. We're seeing tools like Esri that allow developers to analyze thousands of variables at once.
Like what?
They overlay fiber optic routes, grid capacity maps, workforce availability, flood zones, seismic hazards, all onto these massive interactive maps.
So instead of a team of surveyors taking 6 months to create a feasibility study, the software just highlights a patch of dirt and says, build here.
Essentially, they can identify a viable parcel of land in minutes. It compresses months of feasibility studies into a single query. It's like having a God view of the world's infrastructure.
Okay, let's say the GeoAI finds you a spot in Iowa. You still have to power the thing. And we touched on this, but I want to drill down on the energy demand. A single ChatGPT query takes about 10 times the electricity of a standard Google search.
That's the multiplier. And when you aggregate that across billions of users and agents, global demand from data centers is projected to surge 160% by 2030.
160%.
The grid simply cannot keep up with that curve using traditional methods. Renewables are great, but they are intermittent. The sun doesn't always shine, the wind doesn't always blow. AI needs baseload power. It needs to run flat out, 24/7, 365.
So the tech industry has decided to take matters into its own hands. And this brings us to what the articles are calling the nuclear renaissance.
It is a full-blown pivot. We are seeing big tech companies effectively becoming nuclear power operators.
And it's the biggest names. Microsoft is restarting 3 Mile Island to get 835 megawatts. Amazon is partnering with Energy Northwest. Google has a pipeline for 500 megawatts. But help me understand the difference here. Microsoft is restarting an old plant, but Amazon and Google are talking about SMRs. What's the distinction?
Well, the restart at 3 Mile Island is about speed. That infrastructure exists, the concrete is poured, they just need to turn it back on.
Right.
But you can't build a new 3 Mile Island quickly. Those traditional plants take decades and cost tens of billions. SMRs, small modular reactors, are the new hope. They are designed to be factory-built modular units.
So it's like the difference between building a cathedral on site versus a Boeing 747 in a factory.
That's a perfect analogy. You
Yeah.
build a reactor in a factory, truck it to the data center, and install it. It significantly reduces the construction timeline and the cost.
But even SMRs are a few years out. In the meantime, the reports mention a lot of behind-the-meter generation. That sounds a bit jargon-heavy. What does that actually mean for the grid?
Behind the meter means the data center generates its own power on-site and consumes it directly, without that power ever touching the public utility grid.
So they are unplugging from the rest of us.
Or never plugging in to begin with.
Yeah.
Look at xAI's Colossus cluster. They're using dozens of gas turbines right there on the property. OpenAI's Stargate facility is planning over 300 megawatts of on-site power.
So they're like their own sovereign utility providers.
It feels a bit like that.
Right.
But interestingly, the expert commentary in our sources suggests the opposite might happen. They talk about data centers becoming grid citizens.
Okay, grid citizens, what does that mean?
This is a really clever concept, and it solves a major engineering problem. As we retire old fossil fuel plants and replace them with wind and solar, the power grid loses something called physical inertia.
Okay, physical inertia. I'm picturing a physics class. Explain that in terms of keeping my lights on.
Okay, imagine a giant, heavy merry-go-round spinning. That's a traditional steam turbine in a coal or gas plant. Because it's so heavy and spinning so fast, if there's a sudden blip in power demand, like everyone turning on their AC at once, the momentum of that heavy metal keeps spinning, smoothing out the glitch.
That's inertia.
That's inertia. Solar panels don't spin. They don't have that momentum. So as we add more renewables, the grid becomes twitchy. It's less stable.
I see. So how does a data center fix that? They don't have steam turbines.
No, but they have massive backup batteries, BRS systems, just sitting there in case of a blackout. Usually these batteries do nothing. Now, they are using software to provide synthetic inertia.
Synthetic inertia.
Yes, they can detect a wobble in the grid's frequency and instantly, in milliseconds, pump energy back into the grid or absorb excess energy to stabilize it.
So they're acting like that heavy spinning turbine, but digitally.
Exactly. They are turning a cost center giant batteries that just sat there doing nothing into a revenue engine that helps keep the lights on for everyone else.
That is a brilliant flip. Instead of just draining the grid, they act as a shock absorber. Now, we have land and we have power, but there is a byproduct of all this power usage, heat, a massive amount of heat.
It's the unavoidable waste product of computation. Every watt that goes in must come out as heat.
And the report says we have hit the physical limit of air cooling.
We have. Blowing cold air over a chip just doesn't work anymore when the density is this high. So 2026 is the year liquid cooling became the standard.
It had to.
When a single chip uses over 1,000 watts, which is where the new Blackwell chips and their successors are, air is just too inefficient at moving that heat away.
Yeah.
You need liquid. Water conducts heat about 24 times better than air.
There seem to be a few ways they are doing this. There's direct-to-chip, which sounds simple enough, pipes running coolant right to the processor. But the one that blows my mind is immersion cooling.
Immersion is a radical shift. You were taking the entire server motherboard, memory, cables, everything, and dunking it into a bath of dielectric fluid.
Dielectric meaning it doesn't conduct electricity, so it doesn't short out.
Exactly. It looks like water, it flows like water, but you can dip a running computer in it and it won't short circuit. And the specific method gaining traction is two-phase immersion.
The visual described here is wild. The fluid actually boils on the surface of the chip.
Yes, the chip gets hot, the fluid touching it boils and turns to vapor. That vapor rises to the top of the tank, hits a condenser coil, turns back into liquid, and rains back down.
So it's a self-contained weather ecosystem inside the server rack.
It is. And it's incredibly efficient because the physical act of boiling absorbs a huge amount of energy.
It sounds messy, though. Sealed tanks, boiling fluid. I can see why some operators might be hesitant.
It creates maintenance challenges. If a server breaks, you have to lift it out of a tank of fluid. That's why there is also a middle ground called spray cooling. Companies like AirSeas have technology where you spray the coolant directly on the components in a fine mist. It uses 80% less fluid than full immersion, which is attractive if you're worried about the cost or sustainability of the fluids themselves.
Speaking of sustainability, there is another waste product being turned into a resource. The heat itself. I love this example from Finland.
Absolutely, right.
Yeah, Microsoft is capturing the waste heat from servers and pumping it into the district heating network.
It's a perfect example of circular thinking. Usually, data centers just vent that heat into the atmosphere, literally heating up the sky.
Yeah.
Here, they capture it to warm homes.
Sure.
That project alone is expected to contribute about 1% of Finland's required emission reductions.
You take the energy, use it for compute, and then use the thermal byproduct to keep people warm in winter. It makes so much sense. Okay, so we have the design. Underground or underwater, powered by nuclear, cooled by boiling fluid. Now we actually have to build the thing, and we need to build it fast.
Speed is the enemy of quality, usually. But here, they are trying to do both because the demand is exponential.
The report says building one of these AI factories takes about 1,500 skilled workers, but we aren't building them like we used to.
No, stick building, where you cut lumber and pour concrete on site, is too slow. It's all about modularity now. The Open Compute Project, or OCP, has set standards that allow for prefabricated power blocks and cooling skids.
So the cooling system is built in a factory in Texas, put on a truck, and then just plugged in at the site in Ohio.
Exactly. It's like clicking Lego blocks together. And once those modules arrive, the robots take over.
Yeah.
We are seeing digital twins becoming standard practice.
Define digital twin for us. Is that just a 3D blueprint?
It's much more than a blueprint. It's a dynamic virtual replica of the entire facility. Before they pour a single drop of concrete, they build the whole thing in a simulation. They run scenarios. What if a pipe bursts? What if we move this wall? Then, on the actual job site, robots use that data to mark floors and place anchors with centimeter-level accuracy. It cuts operating costs by 10 to 20% because you eliminate human error and rework.
But you still need raw materials. And concrete is a huge source of carbon emissions. I saw Microsoft is using something called electrochemical cement.
From a company called Sublime Systems, this is big because traditional cement kilns are massive CO2 producers. They burn fossil fuels to heat limestone. This new tech uses an electrochemical process at ambient temperatures.
So no kilns.
It's all part of reducing embodied carbon.
Yeah.
That is, the carbon footprint of the building itself, not just the electricity it runs on.
However, there's always a bottleneck. It's never that easy. And right now, the bottleneck isn't just chips. It's transformers.
Oh, the supply chain crisis for electrical infrastructure is severe. I cannot overstate this. Lead times for high-voltage transformers are currently over 3 years.
3 years. So you can build the nuclear reactor, dig the cave, get the robots, and then you sit there for 3 years waiting for a transformer to plug it in.
Pretty much. And the problem is complexity. There are something like 80,000 unique configurations for these things. You can't just mass produce them easily like iPhones.
Which is leading to some high-tech workarounds. The notes mention solid-state transformers.
Right. This is where companies like SolarEdge and Infineon are collaborating. Instead of using massive coils of copper and iron, they are using silicon carbide SiC chips to handle the voltage.
So they're smaller, more efficient.
And crucially, they can handle the weird, bursty power loads that AI creates much better than old-school hardware.
It seems like every part of the old grid is being reinvented, but this supply chain issue, it's not just a commercial headache. It has become a national security issue, hasn't it?
Absolutely. If you can't power the data centers, you lose the AI race.
Yeah.
It is that simple. That's why we saw that massive $550 billion technology deal between the U.S. and Japan.
Mitsubishi Electric and TDK Corp. Coming in to overhaul the U.S. electrical infrastructure.
It's a recognition that the U.S. domestic supply chain can't do it alone. We need Japanese industrial capacity to keep the lights on. It's incredibly geopolitical.
It really is. But let's bring it back to the people. We mentioned robots, but we still need humans to design and run these places, and apparently we don't have enough of them.
The skills gap is at 98%. That means 98% of organizations say they can't find the people they need.
Wow.
And think about the job description we've just outlined. We need people who understand liquid cooling chemistry, high-voltage DC power, and AI network fabrics.
Those are 3 very different degrees.
Exactly. A chemist, an electrician, and a network engineer walk into a bar. And you need all of them to be the same person.
So we are seeing these 10-day intensive boot camps popping up, like the ones mentioned in Nairobi, specifically for power systems engineering.
It's a whole new career path that didn't really exist a few years ago, a necessary pivot. But regulation is also playing a huge role in where these skilled people are deployed and where the concrete gets poured.
Right, a real divergence between the U.S. and the EU.
It is. The U.S. SPEED Act of 2025 is all about acceleration. It cuts red tape, limits environmental reviews, specifically NEPA reviews, and gives Fast 41 status to projects over 100 megawatts.
So the government is saying, build it now, ask questions later.
Basically. Whereas the EU AI Act, which becomes fully applicable in August 2026, is focused on safety and transparency. It mandates human-in-the-loop controls and rigorous safety assessments. It represents a slower, more cautious approach.
And that could drive the actual physical infrastructure to different places.
It's very possible you'll see the big, messy, power-hungry factories built in the U.S., while Europe focuses on the software or governance layer.
So we have looked at the current state of 2026, but the report ends with a look at the future horizon 2027 and beyond, and it suggests the game is about to change again.
Yes. Right now, in 2025 and 2026, we're in the training phase. We are building massive, centralized brains, We put them in caves or near nuclear plants because they don't need to move, they just need to learn.
But that's not the end goal.
No. Starting in 2027, the industry expects a shift to inference.
Inference is when we actually use the AI, right? Like when I ask ChatGPT a question and it answers.
Exactly. Training is reading the library, inference is answering the test question, and for inference, you need low latency.
Right, speed.
You can't wait for your data to travel halfway across the world to a massive cluster in Virginia and back just to tell you the weather, or, more importantly, to tell a self-driving car to brake. You need the compute to be close to you.
So instead of these giant centralized Death Star data centers, we are going to see what?
Edge AI factories. Smaller modular data centers located in hospitals, retail distribution centers, logistics lines. We are moving from a few massive brains to a distributed nervous system spread across the entire planet.
That is a wild image. We've gone from limestone caves to boiling fluids to a distributed nervous system.
It really is an industrial revolution in every sense of the word. We are rebuilding the world to accommodate a new species of intelligence.
So, to recap what we've uncovered today, we are building utility-grade plants that rival small cities in power consumption. We are reinventing the power grid to handle them, turning to nuclear and synthetic inertia. We are changing how we build with robotics and green concrete, and we were seeing a geopolitical scramble to control the supply chain.
And the scale is just going to keep increasing. The sources project global data center capacity hitting 200 gigawatts by 2030. That is doubling our current capacity in just 5 years.
Which leaves us with the final thought to chew on. If compute power is becoming a utility as vital and massive as water or electricity, how does that change the balance of power in the world? We talk about GDP, but are we moving toward a world where a nation's gross domestic compute matters just as much?
It's a valid question. When the ability to process intelligence becomes a physical resource, the countries that can generate and house that power will have a distinct advantage over those that can't. It's a new oil.
Something to think about next time you see a blinking cursor waiting for an answer. That cursor is backed by a nuclear reactor and a boiling bath of fluids somewhere. Thanks for listening to this deep dive into the physical reality of AI.
It was a pleasure.
See you next time.